In this video, I will introduce the concept of electric energy. We will learn how to calculate the energy from various charge distributions, from a point charge, a set of many point charges, a line charge, a surface charge, or a volume charge distribution. We will see two ways to calculate the electric energy, either from the charge distributions or from the electric field. And we are going to get a new understanding on the electric potential and its relation to energy. But first, we will discuss the work that is needed to move a charge. So let's suppose that we have a set of static point charges, and those charges create a static electric field. And in that static electric field, we want to move a test charge from point A to point B. But before the charge is moved from A to B, the first question we can ask ourselves is, what is the force that the source charges exert on the test charge, for example, when the test charge is at point A? Now, in the previous lecture, we have already introduced the concept of electric field to answer this question. Right? Remember, the electric field, E, is the force per unit charge that would be exerted on a test charge. So the force on the test charge is F equal QE, where Q is the test charge and E is the electric field created by the source charges. So if there is a force on the test charge, the test charge is accelerating. And if you want to keep the test charge at a specific position, you will need to exert a force. And what is the force you need to exert to keep the test charge at a specific position? Well, you need to counter the force from the electric field, so you need to apply minus QE. Now, if you move the charge from A to B, you will need to exert this force at any point during the displacement. And so the total amount of work during the displacement from point A to point B is given by the integral of the force F dot the displacement dl. So replacing F by minus QE, that is minus Q times the integral from point A to point B of E dot dl. And last lecture, we saw that in static, because the curl of E is 0 in static, the integral of E dot dl does not depend on the specific path. It only depends on the point A and point B, but not on the path in between. And we introduced the electric potential so that the integral of E dot dl can be written as minus VB minus VA. So after cancelling the two minuses, the work is Q times VB minus VA. So we see that the work does not depend on the path, which indicates that the electrostatic force is a conservative force. This also gives us a new understanding of the electric potential. Now you can write VB minus VA as W over Q. So you see that the electric potential V is energy per unit charge. And because the electrostatic force is conservative, we can consider the source of field as part of the system so that the energy is potential energy. Now, usually the reference potential energy is taken at infinity. So we can write the equation with point A being a point at infinity and point B being a point at the position R. So we have VR minus V infinity equal W over Q. And taking the convention that V at infinity is 0, then VR is W over Q. Again, the electric potential V is potential energy per unit charge. This is our first important result about electric energy. It is that energy is QV, or V is energy over Q. That's the equation. Now let's look at what it means. So for this, I come back to the field created outside a charged spherical shell. Right? Remember, so the black arrows represent the electric field. The shell has a positive charge in this example, so the electric field is pointing away. And first we saw that the electric field decreases as 1 over R squared. And then we saw that the electric potential decreases as 1 over R. Now, we just learned that the energy to move a charge is Q delta V. So to bring a positive charge, the energy I will need is Q delta V with Q positive. If I move the charge towards the shell, V is increasing, so delta V is positive. I need a positive amount of energy. If I move the charge away from the shell, V is decreasing, so delta V is negative. I need a negative amount of energy. That is, energy will be released. In that case, when Q is positive, you can really think of this in the same way as you think of gravitational potential energy, in the sense that the positive charge will tend to go towards the minimum electrical potential. It will decrease its electrical potential, and it will decrease its electrical potential energy. Now, let's consider the case where the spherical shell has a negative charge. In that case, the electric field is pointing towards the shell. Again, the electric field is decreasing as 1 over r squared, and we saw that the electric potential goes as 1 over r, but this time it is negative. So if we bring a positive charge towards the shell, the energy will be negative, energy will be released. Again, the positive charge tends to minimize its electrical potential. If I move the positive charge away from the negatively charged shell, the electric potential increases, the electric potential energy increases, and I need to provide positive energy to move it. Now, let's look at another example that we also discussed previously. It is the field created by an infinite plane. So if the charge per unit surface sigma is positive, then we saw that the electric field is pointing away from the plane, and we saw that it is uniform, that is, it does not decrease as you move away from the plane. Right? In that case, we also saw that the potential is linear and goes as minus z, where z is the distance from the plane. So if I want to move a positive charge closer to the positive charge plane, I will need to increase the electric potential, increase the electric potential energy. I will need to provide positive energy to do that. If I want to move the positive charge away from the positively charged plane, I will need to provide negative energies, that is, energy will be released, and you see that the electric potential is decreased. So in this example, again, the positive charge tends to decrease its electric potential. If the infinite plane has a negative charge, then the electric field points towards the plane. And so in that case, the potential goes up away from the plane. So if I move a positive charge towards the plane, I will do negative work. It will release energy. Again, the positive charge tends to minimize its electric potential. And if you move the positive charge away from the plane, you will have to provide positive energy in order to increase its electric potential and in order to increase its electric potential energy. So in all of these examples, the positive charge will move towards the minimum electric potential, and this is because when Q is positive, W and delta V have the same sign. So decreasing the potential energy is the same as decreasing the electric potential. Okay, but what if the test charge now is negative? So I will take the previous example and show the negative charge in green color. So this time, to move a negative charge away from the positive shell, I will need to provide positive energy. The electric potential will decrease, but because Q is negative, the electric potential energy will increase. Instead, the direction that will decrease the electric potential energy is when the negative charge moves towards the positive shell. So for a negative charge, it will tend to move towards the higher electric potential. It's confusing, but you already knew all of this, right? The flow of electrons in a circuit is from negative to positive. Right? So electrons tend to increase their electrical potential, but this is to decrease their potential energy. Now, before we move on, I have a question for you. So consider a parallel plate capacitor that has a charge plus Q on one plate and a charge minus Q on the other. The plates are isolated, so the charge Q cannot change. Now we pull apart the plates. Does the total electrostatic energy stored in the capacitor increases, decreases, remain constant, or does it depend on how much we pull the plates apart, or there is not enough information and it depends on something else? Okay, if you answered A, then you are correct. The energy increases, and there are many ways to get the correct answer. For example, you know that plus Q and minus Q attract each other, so to pull them apart, you need to do some positive work. Right? Where does the energy that you are doing goes? It goes into electrostatic energy, so the electrostatic energy increases. Now, if you want to put this in the context of what we just discussed, the positive plate will increase its energy if it is in a higher potential. Where is the maximum potential from a negative plate? It is at infinity. So for the positive plate, it will have higher energy at infinity from the negative plate. And the negative plate will increase its energy if it is in a lower potential. Now, where is the lowest potential from a positive plate? Again, it is an infinity. So for the negative plate, higher energy at infinity from the positive plate. So pulling the two plates apart increases the electrostatic energy. Okay, now that we know the energy to move charges, we're going to discuss the energy in a charge distribution. And first, we will just do a distribution of point charges. So suppose we have 4 charges at position R1, R2, R3, and R4. What is the electric energy of this point charge distribution? So first, there is the energy to create point charges from vacuum. So let's call it U0, the energy to create the n charges at infinity. Later, we will see that this U0 is in fact infinite. Now I need to calculate the energy to move those charges from infinity to their position at R1, R2, R3, and R4. So first we will bring the charge Q1 from infinity to the position R1. Now, because this is the first charge, it is easy. The work to bring the first charge is 0 because there is no electric field, so there is just no force on this charge. The fun starts when we bring the second charge. Right? Now we have the electric potential due to the first charge. So the work to bring the second charge is Q2 times the potential from Q1. And we take this potential at the position of R2. So that potential is 1 over 4 pi epsilon naught, Q1 over curly R12, the separation between R1 and R2. Okay, now we bring the third charge Q3 from infinity to the position R3. So now we have the potential from Q1 and from Q2 that we have to evaluate at the position R3. So we have Q3 times this potential, which is 1 over 4 pi epsilon naught times Q1 over curly R13 plus Q2 over curly R23. Curly R13 is the separation distance between R3 and R1, because what matters is the potential from Q1 at the position of R3. And curly R23 is the separation distance between R3 and R2 for the potential from Q2 at the position R3. Finally, I bring the charge Q4 from infinity to the position R4. So I have Q4 times the potential from the other charges, Q1, Q2, and Q3 at the position R4. So in the potential, I have Q1 over curly R14 plus Q2 over curly R 2, 4 plus Q3 over curly R 3, 4. So in total, I have U naught plus 1 over 4 pi epsilon naught, Q1, Q2 over curly R 1, 2, plus Q1, Q3 over curly R 1, 3, plus Q1, Q4 over curly R 1, 4, plus Q2, Q3 over curly R 2, 3, plus Q2, Q4 over curly R 2, 4, plus Q3, Q4 over curly R 3, 4. Now we can write this in a more compact form. W is equal to U naught plus the sum of Q sub I with I from 1 to n times the sum of Q sub j over curly R ij, with j larger than I. This j larger than I in the sum is not super convenient, so another way to do this is to sum over all of the j's different from I. So, but in that case, every term is counted twice, so you add a factor 1/2. The last sum times 1 over 4 pi epsilon naught is in fact the potential from all the other charges. So let's write this potential V at position Ri is equal to 1 over 4 pi epsilon naught, sum over j goes from 1 to n and j different from I of Qj over curly R ij. Look at this formula for a few seconds and get convinced that this represents the potential at the position Ri from all the charges except the one at Ri. This potential does not depend on Qi. It depends on all the other charges Qj, but not on Qi. But it depends on the position Ri because that position is in all the curly Rij. Now, once this is clear to you, then the energy of the point charge distribution is U naught plus 1/2 times the sum of I from 1 to n of Qi times V at Ri. Now, before we move on to continuous charge distribution, I have a question for you. First, consider 3 identical charges plus Q located at the vertices of an equilateral triangle. So all the charges are plus Q, so they repel each other. And if we let one go away, how much energy will it have? What would be the final kinetic energy of the top charge if you released it while keeping the other two fixed? Okay, if you answered C, then you're correct. The final kinetic energy would be 1 over 4 pi epsilon naught 2 Q squared over A. And to find this, let's suppose that you only have the 2 charges at the bottom. How much energy do you need to bring the third one? As we just discussed, it would be Q3 times the potential at R3 that comes from the other 2 charges. The potential follows the principle of superposition. It will be the potential from the charge Q1 plus the potential from the charge Q2. That is 1 over 4 pi epsilon naught Q1 over A plus 1 over 4 pi epsilon naught Q2 over A. And since all the charges are plus Q, you get the answer C, 1 over 4 pi epsilon naught 2Q squared over A. Now here is another question. What would be the final kinetic energy of the top charge if you released all 3? All right, this time if you answered A, then you're correct. Some of the energy has to go to the kinetic energy of the other charges, so it makes sense that it is less, but it is not 1/3, right? To find out why, let's look at the total electric energy. As we learned, it is given by U0 plus 1/2 of the sum over the 3 charges, 1, 2, and 3, of Qi times the potential from the other 2 charges, V at Ri. So Qi V at Ri is the same as the previous question. It is 1 over 4 pi epsilon naught 2q squared over A. So the sum is 3 times that. And now we can simply we can simplify the 1/2 times 2. So we end up with U0 plus 3 times 1 over 4 pi epsilon naught q squared over A. Now the U0 is the energy to create 3-point charges at infinity. So this part does not convert back to kinetic energy when the charges are released, so we can ignore it. So the next term is 3 times the energy per particle that can be converted back to kinetic energy. So each particle will have kinetic energy of 1 over 4 pi epsilon naught q squared over A. That is answer A. Now we're going to discuss the energy of a continuous charge distribution. Before, let's summarize what we found for point charges. The energy is given by U0 plus 1/2 sum of Qiv, where V is the potential from the other charges. And now we're going to extend this to the case of a line charge distribution. To go from point charges to continuous charge distributions, we change the sum into an integral. We have already used this to calculate the electric field from a line charge. We have already used this to calculate the electric potential from a line charge. So I can go faster now. We use the same trick for the energy. So what we do is that we replace the sum over Qi into an integral over lambda dl. So the energy becomes 1/2 integral of lambda v dl. Now you may wonder what happens to the U0. It is a little bit subtle for now, but basically it takes an infinite amount of energy to create a point charge with a charge Qi, but it takes 0 energy to create a charge lambda dl because dl is infinitely small. And if you're not convinced with this argument, just accept it for now, and we're going to revisit this later. Now, for a surface charge, we use the same method. The sum over Qi is replaced this time with an integral over sigma dA. So the energy of a surface charge distribution is 1/2 integral of sigma v dA. And for a volume charge distribution, the integral is over rho d tau. So the energy of a volume charge distribution is 1/2 integral of rho v d tau. Now, similarly to all the formulas that we're going to see in this class, you should not remember all of them. You should just remember one and know how to get the other ones, right? So for example, just remember the energy of a volume charge distribution, and you know that for a surface, you use sigma dA. For a line, you use lambda dl. You don't need to remember all of those. So we found that we can calculate the energy of a charge distribution if we know the charge density rho and calculate the potential V. Then the energy is just 1/2 integral of rho v d tau. Now there is another formula to calculate the energy from the electric field. I will show that the energy is 1/2 epsilon naught times the integral of the whole space of E squared d tau. So for this, we start with our formula with the charge density rho, and we use Gauss's law that says that the divergence of E is equal to rho over epsilon 0. So we replace rho by epsilon 0 times divergence of E. Then we will integrate by part. So we replace nabla dot E times V by minus E dot nabla V plus nabla dot EV. So the first integral has E dot gradient of V, and minus gradient of V is electric field E. So we end up with the integral over E squared. At this point, the integral is over a volume, so it is integral over volume V of E squared d tau. For the second integral, we have integral over a volume also of a divergence. So according to Green's theorem, we can replace this by the integral over the surface boundary without the divergence operator. So the second integral is integral over the closed surface boundary of the volume of E times V dA. The final step is to get rid of the second integral by extending both integrals to an infinite volume with an infinite surface boundary. So what does the second integral look like if the volume we consider is all of space? Then the boundary is at infinity. So we know that the electric field created by point charges decreases as 1 over r squared. Even if we don't have point charges, as long as the distribution of charges has a finite size, very far away, it will look like a point charge. So the field will decrease as 1 over r squared. Again, maybe you're not convinced that I can treat any finite charge distribution like a point charge when I'm very far away from them. And we will, in fact, discuss this in detail later on in this class. For now, just accept that it is either 1 over r squared or something even smaller. Similarly, for the potential, we know that it is in 1 over r. And remember, we take the potential to be 0 at infinity, right? And the area goes as r squared. And so in total, I have 1 over r squared times 1 over r times r squared. So 1 over r. So the integral goes to 0 if the volume goes to infinity. So if we integrate over all space, we only have the first integral, and the energy is 1/2 epsilon naught integral over all space of E squared d tau. We now have two ways to calculate the energy of a charge distribution, one from the electric field and one from the charge density. So let's do an example. Find the energy of a uniformly charged spherical shell of total charge Q and radius r. As we just saw, we have two ways to do that. First method, we can use the integral over the charge distribution. Here we have the surface of the shell, so W is 1/2 integral of sigma V dA. And the second method is to integrate the electric field. W is 1/2 epsilon naught integral over all space of E squared d tau. So now I will pause a little bit and let you do this on your own as an exercise. If you do this correctly, of course, you should find the same answer with both methods. All right, let's start with the first method. So we already know the potential on the surface. It is 1 over 4 pi epsilon naught Q over r, where r is the radius of the shell on the surface. The potential is uniform on the surface, and we can take it out of the integral. So the energy is 1/2 1 over 4 pi epsilon naught Q over r integral of sigma dA. But integral of sigma dA is simply the total charge of the shell, which is Q. So the energy is 1/2 Q squared over 4 pi epsilon naught r. Now let's do it with the second method. Previously, we already found the electric field from a spherical shell. Right? We found that the electric field inside is 0, and outside it is 1 over 4 pi epsilon naught Q over r squared along r hat. So we only have to integrate outside because inside it is 0. And now we take the square of the electric field, and the constant can be taken out of the integral also. So the only thing that is left under the integral is 1 over r to the power 4. Now, for this, it is convenient to use the spherical coordinates. So the small element of volume d tau is equal to r squared sine theta dr d theta d phi. Now, the integral of sine theta over theta will give me a 2, and the integral over phi will give me a 2 pi. So I have a factor of 4 pi. And I only have the integral over r, where r goes from big R, the radius of the shell, to infinity, integral of 1 over r squared dr. So this integral is simply minus 1 over r between r and infinity. And so in the end, the energy is equal to 1/2 q squared over 4 pi epsilon naught r. And of course, the two methods give the same result. A note here, you see that a point charge is like a shell with r equal to 0. And you see that for a point charge, you would have 1 over 0. So the energy to create a point charge would be infinite. Now, before we conclude, let me add a couple notes on electrostatic energy. The first one is what I just said. The energy to create a point charge is infinite. In practice, what this means is that a real point charge cannot exist, right? It would take an infinite amount of energy. So in reality, we must have a finite size for a charge. And the second comment is that we have two methods to calculate the energy. One where we integrate over the charge distribution, and one where we integrate over all space. So one question you might wonder at this stage is, where is the energy stored? It is stored in the charges, or is it stored in the electric field? So we don't have the tools to distinguish yet. For this, you will have to wait until you take the next class, Physics 110b. But I can tell you the answer. The energy is stored in the electric field. And finally, the last comment is that the energy does not obey the principle of superposition. And you can see this directly using the formula with the electric field. If you have two charges when creating each creating an electric field, you know that the electric field itself is E1 plus E2, but the square will have E1 squared plus E2 squared and an additional term 2E1 dot E2. And so the energy is W1 plus W2 plus an additional term which has the integral of E1 dot E2. And so you see that the energy of two charges is different from the sum of the energy of individual charges. And the two charges interact with each other, and so the total energy contains an additional term. So let's summarize what we learned in this video. We introduced a new way to think of the electric potential in terms of a potential energy per unit charge. The energy for moving a charge can be given as the charge times the difference in potential. So for positive charge, it will tend to lower its electric potential energy by going towards lower electrical potential. And for a negative charge, it will tend to lower its electric potential energy by going towards higher electric potential. Then we saw how to calculate the energy of a distribution of point charges. It is U naught, the energy to create a point charge at zero potential, plus 1/2 of the sum of the charges times the potential from the other charges at that point. And then we generalized this to continuous charge distributions. For a volume charge distribution, the energy is 1/2 the integral of rho v d tau, and similar expressions for a surface charge distribution or for a line charge distribution. And finally, we saw that the electric energy is in the electric field, and we derived an expression for the energy in terms of the electric field, 1/2 epsilon naught integral of E squared d tau. And in this case, the integral is over all of space that has a non-zero electric field. And we mentioned that unlike electric field and potential, there is no principle of superposition for the electric energy. Now, there is more to say about electric energy, but before we need to discuss materials, conductors and insulators. And that will be the topic of the next lectures.